reflecting a little bit on the arc of our traversal of material yesterday. Yesterday began with some reflections in response to student questions on model scope. And I noted the importance, in my view, almost the primacy of considerations of structuring considerations of model scope with a threefold division in mind. I use slides to illustrate it there, and I won't call those up again, but you'll recall that it distinguished things that were produced by the model, generated by the model, that the model told us about, and were per forte represented in the models. The models generating them, calculating them. In yesterday's model of community mobility, this included not only things explored in some previous models within this event, things like burden of infection or burden of chronic disease more generally, burden of disease more generally. But it also included matters yesterday of sort of travel times between one point and another, which were mediated by, well, Euclidean distance and at first, but then geographic routing, street networks, the existence of street networks and connectivity. Within model of community mobility, networks themselves are dynamic constructs that are persistent only for a matter of hours and then shift as an individual moves between contexts. Those are generated by the model as well. And these generated phenomena frequently exhibit those hallmarks of complexity, those outcomes of complex systems that I spoke about in my opening lecture in this boot camp. I noted there that there were these underlying features of complex systems, characteristics of complex systems: nonlinearity, path dependence, the occurrence of heterogeneity in the system, connectivity patterns, underlying processes that exhibited different levels of delay, feedbacks, oft competing or interacting. The presence of state that varies sort of as accumulations driven by other processes you could view as a feature of the underlying system. And those gave rise, induced behavior that exhibit properties of complexity, things like lock-in effects and tipping points, and factors involving counterintuitive behavior and effects of intervention that are diverse and multifaceted across the system and are often delayed from that initial intervention. and that often blow back and push back against that intervention. Or combine to make its effects change over time, to resist it, to adapt to it. And most of those factors that we're thinking about there are endogenous. They're given rise to by those properties of the system. And in ABMs, the particularly broad set of features, again, with mobility or network structure, people's location being generated over time, not being pre-specified by us. And then in the second category, there are things that are in the model they're represented in the model explicitly. And they have effect often on the endogenous thing, but they're exogenous. The things that we pre-specify, we dictate. And there too, our experience yesterday had lots and lots of examples. In fact, when you bring in GIS information, broadly, that's bringing in a set of structure that impacts the model, but it's pre-specified, right? It's not generated by the model. And then it shapes model structure. It shapes model evolution. The occurrence of a bridge over the South Saskatchewan River means that people can be routed more quickly from one point to another than would otherwise be the case. The location of a given school affects the catchment basin of kids who attend it. Indeed, the bounding area of the city ends up impacting the emergent dynamics, but is pre-specified. But there are many features beyond that, of course, or very imposition of certain assumptions involving duration of infection. Mean time until immunity to the infection wanes, the contact rate, the probability of transmission given discordant contact, all of those were imposed on the model as assumption. They were represented, they were conceptualized, and their impacts were characterized, but they were exogenous. So rather than sort of distinguish, and the final set of things I should say are ignored, and again, many of those, but invariably not all, are consciously put aside. But then there's going to be some unknown ignored things, which we haven't thought about, and which maybe other stakeholders bring to the table. And that's not in the model right now, but it could be, and we can add it to the parking lot of things that are considered for later incorporation. So rather than distinguishing is it in scope or out of scope, we make this threefold division, and it's a very useful division. And I have noted in some of my remarks that when it comes to endogenous things, it's worth noting that within ABMs, quite a large fraction of those are epiphenomenal. They don't govern the model dynamics. Rather, they reflect it. They emerge from it. They're part of a data generating process that rises up. So we talk about observer processes and reporting. And those processes and the data that they calculate the summary measures, etc., are profoundly important within the learning process. But at a technical level, they're not part of the what defines the model's evolution as a dynamical system. So they're a different sort of type of dynamics. It comes out of but doesn't go back into the dynamics of the system itself. It doesn't drive the dynamics of the system. So we'd started with a reflection on that, and I did want to sort of further emphasize, because when it comes to GIS, it's easy to be confused, like, where does this fit in? We brought in that GIS model towards the end yesterday, these GIS features. And it's worth noting that those, like many other features of the model, are imposed as exogenous features. Now, again and again in this boot camp, and again in my teaching more broadly, I emphasize this point of structure drives behavior, a common slogan within system dynamics, with good reason. And that structure drives dynamics that where what is happening over time is shaped in profound ways by that structure, not merely by the data that goes into the model. There's sometimes a misconstrual of models as just these kind of sieves where you pour in data and outcomes data, and if you pour in garbage, you get garbage out. But the structure in the model, which is often captured from broader understanding, grounded theory, etc., shapes hugely what's possible. And it's not at all the case, this common myth, that you can make anything come out given by choosing what goes in as data. That's far from the case. The model structure shapes the modes that are possible. And I did make that point yesterday at one juncture. When we were exploring different modes of behavior that could come from a community spread of infection. And I noted that the structure of the model, while for particular runs we were exploring, led to an outbreak that crested and came out and disappeared, that it was possible to get patterns that were quasi-cyclic, that weren't perfectly regular, but exhibited sort of these regularities of successive waves. And we ended up, in fact, capturing those. But structure in these ABMs, it bears emphasis, it's a somewhat more, it's in the current forms of ABMs, and I'll use AnyLogic as one that actually is a little bit better bringing out that structure in state charts compared to many where that structure of state charts would be hidden in code and it wouldn't be obvious. It'd be a bunch of if statements and functions and loops and so on, which would obscure that structure, the fundamental structure there. AnyLogic, to its credit, brings out certain types of structure, and that's one of them. But there's many other types of structure that apply in ABMs that shape model evolution. The form of a network that's imposed, the fact that we imposed a distance-based network on a rules of crowding and not a random Poisson random network where any two people across the space were connected with an equal probability. We assumed people were mixing equally. Or some sort of scale-free network where certain individuals were hubs and others and most had very few connections, as insightful as that could be. Or a small world network where it was mostly local connectivity, but some people are connected far away. The dynamics would have been rather different. We wouldn't have had those islands just disconnected if we had had global connections that could have reached them. And the wealthier individuals, like the poorer ones, could have felt the sting of infection. So networks are an important element of structure. And in fact, as you'll find lectures by me, many online, where I emphasize the structure and the resulting dynamics of the networks, talking about the characteristic dynamics you see, how profoundly different it is in the case of purely local connectivity, say a ring lattice network, or in 2D space, a distance-based connection network, where it's purely local. I'm connected just with immediate neighbors in space. Comparing that with what we see in a small world network, or what we see in a Poisson random network, or what we see in a scale-free network. Structure there determines behavior as well. So networks are an important part in the network class, and any spatial patterns, for example, which drive it, are a really important part of model structure in ABMs. We saw yesterday that mobility, spatially mediated, like route mediated mobility, this also can be a very important governor of dynamics in ABMs. If we had two cities where it took much longer to go from one to the other, if we have a world where cities are locally tightly connected, but then there are only occasional travel routes, think a ship going from one continent to another, the dynamics of infection spread in that world will look profoundly different than it does in a world where there's no connections at all, or where, you know, there are multiple daily connections from any big city to any big city with airline travel. So when we have mobility, the character of that mobility and its mediating structures, like routes, road networks, are actually somewhat elements of structure that affect dynamics as well of a model. And then messaging, we see, for the most part, messages spread over network connectivity. And there's a lot of logic, I think you're coming to realize, for better or for worse. In many ways, it's obscuring, in my view, associated with this sort of choreography of sending messages and getting them from others and transitioning and passing them on. It's functional. It reflects to some degree, it mimics to some degree certain types of asynchronous influence, where I might cough and you catch a cold. But there's important logic there that's every bit as important as the logic we see placed before us very explicitly in state charts. And yet those connections, like if we look at that model we were building up yesterday, those connections betweenst, I'm just sharing my screen here, between, say, this infection send where this sends a message, and then some other individual, a neighbor to this person in a network, receives it with this connection. That's a different individual and transitions. That's not made obvious here. That's not made manifest by this diagram, that this catalyzes this, that this message is somehow paired up with this receipt. This is the send, this is the receipt of that message, and that causally one leads to the other in different individuals. That is not indicated very explicitly here. And in my view, and in my actions and in work, better capturing that linkage, that having a language to describe that, a language to show that, a language to make that manifest, make it obvious in a way that then can be critiqued, challenged, improved, so we can collectively learn from it, collectively refine it, is important as a broader commitment to model transparency, right? So here we have a need to try to improve model transparency further when it comes to certain elements of structure that are currently under captured in our diagrammatic mechanisms. And I can't help here but riff off this a bit. We've seen that, or I've alluded to the fact, and we'll see it more fairly soon, that for example, in system dynamics, we have a really rich tradition of using causal loop diagrams. And in the past few years, as some people here know, I've introduced causal loop diagramming to the higher mathematics community, particularly with category theory, and where they become aspects of focused study, and really given lots of extra insight about to me and to a growing number of people about the utility that they offer, about ways to further enhance that utility, about ways to make them more flexible, ways to analyze them with a special richness. And there's a lot of innovation going on in this sphere right now because they are at once transparent and understandable within minutes by people from all walks of life, but also really powerful in the insights that they can generate. And there's a strong tradition of using these diagrams to reason in powerful ways about the dynamics of systems, even when we don't have fully quantified understanding about some of the relationships captured, and most of the relationships captured. And even when we may be dealing with somewhat difficult to quantify phenomena like the occurrence of stigma or the feeling of shame associated with that, or or fear or elements of stress. I'm not arguing that those couldn't be approached fruitfully from some quantitative lens to a degree. I believe they can. But the point is that these diagrams can be used to discuss these challenging factors in a really insightful way without requiring that, and without requiring bringing it all the way to a fully simulatable, fully unambiguous model, sufficiently unambiguous that we can run it. But more than this, they accompany. They can be used to bring insights early and often into a discussion in a way that then builds stakeholder understanding, elicits tacit stakeholder understanding, and elicits experience, can build senses of trust or buy-in or being invested in the modeling process, but can also bring out different perceptions, cases where perceptions are strongly different, and really help document that and do justice to bringing out different voices. One of the things I'm tempted to do in the next 2 days, in the final 2 days of the boot camp, is to really talk about this participatory milieu in greater detail, because I'm highly involved with it, but highly involved in a way that also interfaces centrally with agent-based modeling. And what I'm talking about, and what I wanted to emphasize here is, while we have those tools on the system dynamics side, we don't really have yet a good language for visual language. It's more than visual. We don't have a formal way of characterizing relationships with that level of versatility, flexibility, on the one hand, accessibility on the other, or on the other. We have to start dealing with feet as well here, beyond hands, but also at the same time, in terms of the insights that they deliver. And over the years, this goes back, our work on this probably goes back to about 12, 13 years on building software systems that would let us articulate languages sort of akin to causal loop diagramming for agent-based modeling and for individual-based modeling and thinking. And the idea here is that while causal loop diagrams are very, very powerful for thinking about systems at an aggregate level, often they don't have the language to speak about some of the issues at the heart of our motivations for using individual-based modeling. Multi-scale phenomena which relate to factors within an individual on the one hand, between individuals on the other, and between individuals and environments. They don't have a way of describing mobility-related factors or spatial factors, geographic or not. Network structures and the insights that come from the topology of those network structures, their structure, and the recognition of how profound the impacts of that on dynamics of a system can be. We don't have a language for that in causal loop diagrams. And it's not a criticism of causal loop diagrams. They are exquisite for bringing insights to bear in their own terms. And, I am just thrilled how much attention and um, and rightful uh, sort of advancement they're getting from the higher mathematics community because of our linkage with that community. But the fact is, we need something for these other contexts that's uh, just as versatile, rich, uh, uh, helpful for thinking, transparent, and insightful. And so we started working with back then it was more building up software, uh, collaborative software. This was before Google Docs was perhaps well, certainly before it was very widely used. It was perhaps before it was introduced that we first started doing this um, with the Google Real-Time API. Maybe it was maybe the first edition of Google Docs was out, etc. But we wanted to create a Google Docs for this sort of qualitative model, and we call it um, collaborative qualitative hybrid modeling, um, related to the hybrid models that we built. And you could use state charts, and you could have some things within an agent, and there was a language of events and transitions and parameters for that person. And you could have different types of agents illustrated in this kind of torso and head style. And you know, it maybe looks a bit hokey, but this was a collaborative system that different people could come in and simultaneously build up a little description of this. And by resizing this, you could kind of put more structure inside this agent and other agent. And the idea is you could use it to think through the processes operating without committing to a fully quantitative model. And you could have dialogues about this and have your model be challenged and refined and critiqued and improved by others and you know mimicked by others. And we had stock flow diagrams as part of that hybrid commitment. And you know we evolved this and this I as in so much of my I mean the large swath of my thinking, Jeff McDonald played a really helpful role in sort of um, uh, thinking through these issues and challenging my thoughts and expanding them, etc. And you know, we thought about how we could use this to characterize elements of mobility, characterize relationships between people, having networks as something you could talk about in this context, and frankly, to which people from all walks of life can relate, as our work has demonstrated with people with lived experience of homelessness in past years. Uh, and you know, we might also capture things such as the occurrence of an intervention and feedbacks would be a big part of this. But the language of state charts, as we've seen, affords us a way of kind of describing situations that's extremely powerful to avoid combinatorial blow up, to allow sort of crisp characterization of different concerns, and while still having some flexibility to illustrate interactions between them. So, you know, we tried to work with this idea of sort of a language, and we got we got far enough to convince myself that it's number one, much needed. Number two, the basic idea here is a really good one. Number three, it's a bigger challenge, and it needs to be approached as such in terms of student attention and taking it seriously in funding. And so we still have this, I still have this aspiration. And I wanted to share that it's my own conviction that causal loop diagrams, while they are extremely valuable here, they are um, imperfectly matched to the needs of agent-based modeling projects. They are um, they deliver still a great deal, and we use them enthusiastically to inform those projects, but they lack a level of a a degree of granularity in their description and specificity when it comes to nesting structures, when it comes to networks and spatial location and mobility and interaction person with environment, that really is just beckoning for greater attention. And it's my belief, and perhaps it's motivating this call to action, that we as a group in the field more generally needs to rise to this challenge to really have something similar to the rich tradition of closed-loop diagramming that commonly accompanies system dynamics projects. We need something similar for agent-based and hybrid modeling, which is our bread and butter, because of the profound and transformative impacts it can offer. So I'll leave those remarks on that point, and forgive me for trying to fold that in here, but I think it's an important reflection if one is to try to embrace the full richness of the participatory engagement with models, that we need to think about that sort of qualitative or semi-qualitative modeling that's supported by model mapping of this sort, things like closed loop diagrams. Right. One or two other, maybe two other big points here. So I'm looking, and forgive me, I'm just calling up the requisite slides here. Okay. And here we go. Okay. And I want to make a distinction that I think is, I find it's shockingly it reflects a shocking under-conceptualization on the part of the vast majority of agent-based modelers, and indeed the community that comments on that field, and the need to think more solidly and with greater clarity about the modeling process when it comes to ABMs. I often, show this slide, which goes back upwards of 25 years for stages of the modeling process. And I've inflicted it on you folks, but, where we proceed in an iterative fashion and a cyclic fashion, going back and re-examining things from findings from others, from problem conceptualization, thinking about the scope, etc. Qualitative problem modeling, often these things are often going together. These are can use, this should really say system structure diagrams. State charts can be used in a kind of qualitative way, as we just saw, causal loop diagrams, certainly. But think about the scoping: endogenous, exogenous, ignored, etc. But after that, there's, I think this needs some refinement. There's a thing what's called model formulation, which is sort of, okay, you build the fully specified model, and then you go through some stages of like trying to calibrate it to data, and you learn, and often this is a giant learning opportunity, and often you find the model just structure just will not explain certain types of behavior, and you modify it. There's a lot of stylized modeling projects where this is not part of it. But model testing is another key part, and you can argue which of these comes first. There's a lot of testing you probably want to do along the way before calibration. And then you might use the model for its purposes, which often include policy evaluation, but may be focused on explaining trends or trying to understand the value that come from new types of data sources, or trying to bring people together, or trying to better assess if, a certain pattern you see in the world can be explained by just a few factors. So this is a kind of broad brush attempt to articulate things that go on at different points. But I've become increasingly dissatisfied with my take on this from earlier. And I specifically wanted to sharpen the thinking at the stage of model between here and model formulation, because I think it's a key issue, and it's one that's generally clumped together to bad effect with ABMs. When we conceptualize model, we think about its scope, and we think what's endogenous, what's exogenous, ignore for this version of a model. Again, I want to emphasize the importance of proceeding in an incremental, iterative way. And there's later slides, on this that emphasize centrally the importance of agile or an incremental model development, proceeding in stages. But what I want to emphasize is once you've got a certain scoping in mind, there's generally a need to kind of unpack and need to, like, how am I going to characterize this? Okay, just am I going to characterize people's viral loads, or am I just going to think about them as being in a infected state? Do I want to have a latent state, like an exposed state before an infected state? Do I need to delineate infected, asymptomatic, infected, symptomatic? How much detail do I want? Stages, sort of like I might have with TB, with stages leading up to, cavitary TB, and successively worse, more serious symptoms and transmission prospects. You're going to be wanting to think about that, and based on a certain characterization you come up with this division, you're going to be thinking about things like, okay, there's a certain chance, there's a certain hazard rate governing going from this to this, or there's going to be one animal that can transmit to another, or there'll be a chance that it could pick up bovine foot rot from the manure, or that one individual will be affected by their immediate social network, the prevalence of smoking and that, and their chance of developing, of starting to smoke on a per year basis. So the hazard rate of them starting to smoke will be proportional to the number of people in the network that also smoke, with some offset. So there's kind of unpack it at a mathematical level here. This is not about writing Java code. This is not about writing NetLogo code or code in C++ for Swarm, or code in Julia for agents.jl, or code in Python for Python-based ABM frameworks. This is about sort of mathematically, how am I going to characterize this? It's going to be like a transition among states, or it's going to be like some sort of stock and flow type model, or ordinary differential equation model, or what have you. The network structure, I want to assume. And then there's a need to unpack that into an implementation. And this stage involves some computer programming in today's frameworks, more or less. And I could take the same model formulation, the same idea of the model, the same model design. So I'll often call this an element of model design here. It's a conceptual design of the model. How I implement it will be different for different frameworks. Maybe I could put it into Repast, and I could put it into NetLogo, or I could put it into AnyLogic. I could put it into agents.jl and Julia. And those would be different implementations of the same model formulation. The model formulation is like the mathematical characterization of what I want to capture. And this is like how I implement it as code. Those are different things. And in software, we make a big distinction between these. This is the design. This is like my plan for what I want. This is, and often there's requirements up here which drive that. This is the implementation of that design. There are bugs where the implementation differs from the design. Those are called bugs, or defects. They're mistakes in capturing this design that I didn't capture the design right. I built the model wrong. A problem here where like I have a poorly matched formulation for what I want to capture from my requirements in software. I built the wrong model. I built the model wrong. I built the wrong model. That goes on up here. Those are very different things. And what I find is that people coming to agent-based modeling again and again and again, I find people, excited about agent-based modeling, and they say, okay, so do you have any advice for hiring a Java programmer to do the agent-based modeling? And I tell them, like, don't hire a Java programmer. A Java programmer will completely clueless. A Java programmer will have no idea. I'm using my language sparingly. They will have zero idea about how to do model formulation. They don't know jack about how to describe processes in the world. This is about describing processes in the world, and often processes in a given domain area. So maybe it involves ecosystem health, or involves aspect of communicable disease for people, or veterinary matters involving communicable disease, or veterinary chronic disease, whatever it is. There's often a kind of buildup of knowledge of how we capture these things in that field, and what's a good way of characterizing the stages of TB, latent, primary, plural TB, or early primary, plural, and cavitary, or what have you. There's kind of ways of describing things. Same thing with types of communicable disease that are, shorter term acting, right? Various latent stages, or for STIs, a prodrome stage, and subsequent stages of presentation, or for syphilis stages. And that's about the formulation. And if you hire a programmer, they're not going to have a snowball's chance in hell of being able to do effective formulation. Because by and large, people who do programming have just no clue about mathematical. They have no clue about modeling, of mechanistic modeling. That is its own science. That's different from programming. A Java programmer could say, like, okay, tell me what you wanted to do. That's this, and I'll put it into code. But you got to be really careful, because you want a programmer. If you're going to have someone with programming, you need to have someone who knows some modeling as well. Because otherwise, they're not going to really understand what you want generally, and they'll put something in place. And there's a risk that if you can't, if they do it in a way that many common developers do, many common programmers do, you won't be able to understand it, and you won't be able to know the degree to which these match. So the challenge of modeling, of agent-based modeling for people, in my experience, is vastly overrated this challenge. People got caught up, like, I have to write Java code. I have to learn how to declare a variable. I have to I have to know how to say die, in these contexts. I have to figure out where to put a semicolon or whatever. And look, I'm not lessening that there's some learning going on, but that's not the real challenge, like the substantive foremost challenge with agent-based modeling. The substantive foremost challenge with agent-based modeling, just with system dynamics modeling, just with discrete event modeling, is at this level of sort of how to take a domain, unpack it, divide it up into a plausible exogenous, endogenous, exogenous, ignored division, set the scope, and judiciously choose in an incremental fashion that delivers insight but improves our thinking and goes step by step towards that plan, towards a plan and adds features in and adds elements, components of the system in a prioritized way, sometimes in a way that's driven by stakeholder interests, and gets some results out and discusses them and learns from them, and refines our mental models. That's what's going on in that stage. That is the big challenge here. It's not the programming side. And I have seen some outstanding conceptual modelers and people who have wonderful basic ideas about modeling formulation make the horrible, the defining, the fatal for a project mistake of hiring some programmer. Oh, we need to hire a programmer to do this. It's in repass, so we have to hire a Java programmer, and we'll go have them code it up. That way lies madness. And what I've seen, the result is a nightmare. I teach software engineering in addition to teaching modeling, and I've gone over the code for those projects. It is frightening. It is distressing scientifically because papers published based on these models were not accurately describing what's in fact in the code base, not describing what's implemented in this repast model, which is a big software engineering project built by the software developer. That the modelers don't know what's there, and they don't realize that there are big problems from the standpoint of mismatches between the model implementation and the desired model formulation, or certain lines of code which were critical to model delivering on its promise were disabled temporarily but never re-enabled or what have you, and where the programmer ended up, not testing their code, and so it exhibited bugs. And so going over those code bases is at once software engineering. It's distressing from a software engineering side, but familiar from the world of how bad software can get. But it's much worse scientifically. It was like, what could have been here if there had been a true commitment to model transparency, if there had been the right team involved, if the modelers involved had insisted on working with someone or themselves gotten involved enough that they could have made sure that the implementation was in line with what they wanted, that they were highly enough involved in that instead of outsourcing it to some developer who doesn't understand modeling. What could have been achieved would have been, vastly more than what came about. And it was tragic. It was tragic because there was a mistake made of treating it as a software engineering exercise to build the model, when it should be treated as a and that's no more true than creating lab notebooks and reasoning about scientific experiments is an exercise in penmanship. It's not an exercise in penmanship. It's not merely writing arbitrary words down on a page. It's a scientific process, and we need model formulations that are as close as possible to the implementation. And that's my commitment. It's why I teach with AnyLogic, because it's closer. But you will find in larger models, as Wade will tell you, that there's some growing amount of code that will come in, particularly on the summarization side and some of the logic side. And you have to manage that very carefully. If you have a larger project, you have to make sure that you work very closely. If you have someone hired, you make sure that they have modeling training, and you make sure that they discuss with you as the modeler. If you're not doing it yourself, you make sure they discuss with you what exactly the assumptions are and show you things, and make sure that they document what they have, what they've built, in a transparent fashion so that you can fully understand it. So you can look at it and make sure that it matches your intentions. So you may be wondering why I seem to obsess about intention revealing features of models, why I'm such a stickler about names. Yes, it's because I've been burnt many times in my life, but I've also seen projects fail that had wonderful things to contribute because they didn't pay attention to these matters. And I want our modelers and the model team members, including people with lived experience, to understand absolutely as much as possible through good commenting, good naming, clear visual structure, use of things like state charts to illustrate structure and not hard coding it, as is common in many other frameworks. I want those things to speak to us about what the assumptions are, to make evident when we are making assumptions, what those assumptions are and why. And I want to be able to make sure that the model that is evolving in a way that retains it as a scientific enterprise, and one where the core modeler, the core person directing the project, is always closely attuned to what exactly is in there and what it represents. And if you think this requires you to go out and become a software engineer, that's not the case. If you think it requires you to, take a separate degree in modeling, that's not the case. I do know some very good projects run by domain experts in this way. They are AnyLogic projects. Several of them have involved TAs here, where the domain experts stay very much in tune, very much aligned with what the understanding is that's actually captured in the model. And when there are deviations, it's quickly identified. And that takes a certain commitment to the modeling process, and it's not amenable to kind of a very hands-off view where it's like, oh, that's the programmer's job to go make it happen and to run these scenarios. No, you have to, it's a full contact sport. It's not a spectator sport. It's a sport you have to be, fully invested in. But don't let the fears about computer programming get in your way and make you think that's the primary nature of agent-based modeling. It's not. Agent-based modeling is not a software engineering exercise. When agent-based models become large, it's important to have a really strong commitment to making whatever software engineering is there absolutely as transparent as possible. And it is, I will tell you as a professor of software engineering, it is eminently possible. Don't let anyone tell you otherwise. But it requires people who are committed to that noble cause. So, I'll stop my comments there, but I hope those help in informing some of your understanding on the issue of sort of model teams and model team members and barriers to learning modeling, etc. Okay, so I probably went on too long and that retrospective, but I hope those comments will offer some value.